Okay. Hello, everyone. I'm Yicheng from TDD Institute. Today, I'm glad to introduce how to mitigate astrometric bias in barycentric correction. We know that the Earth's twin can be detected if the accuracy of radial velocity can reach 10 centimeters per second. We need to face a lot of challenges to reach this accuracy. Besides building advanced instruments as introduced by the previous speakers, we need to consider a lot of effects. For example, the star spots would introduce the radial velocity noise for about 1 meter per second, and telluric lines would introduce the noise for about 10 centimeters per second. These topics would be introduced by the speakers in the next 2 days. And data reduction is another challenge for EPRV. One of the main components. You cannot hear. Can you hear me? Hello?
In the room, we can hear you just fine. Yeah, it looks like most people on Zoom are also okay.
Well, maybe
so
it's
Eric, it might be on your end. I'm sorry.
Oh, okay.
But you go ahead and proceed. Thank you.
Okay, so data reduction is another challenge for EPRV. So one of the main components in radial velocity data reduction is the barycentric correction, which subtract the motion of the Earth from the measured radial velocity and to obtain the radial velocity as measured from the heliocenter. In recent years, the barycentric correction has been well modeled to the precision of 1 millimeter per second. So it seems that it's no longer a problem for detecting Earth twins, right? However, these models assumes precise input astrometry. So if the astrometry have a bias, then the line of sight direction, the n hat, would also have a bias. And this bias, delta n hat, or you can say that the bias of line of sight direction would increase linearly with respect to time. This is because the proper motion as a part of the astrometry is also biased. So this delta n would be coupled with the Earth's motion and make a annual noise in the radial velocity result, which is very bad for detecting Earth twins because we know that an ideal Earth twin has exactly the period of 1 year. So you may ask that since the current state-of-the-art astrometry program, for example, the Gaia can reach the accuracy for about 10 microarc second. How can it be a significant bias? This is because when the target star have an unknown companion, they would have reflex motion around their common center of mass, as shown in this picture. You can consider the along scan direction of the Gaia satellite, or you can call this direction the abscissor. The position of the target in this direction will change periodically due to the reflex motion caused by the companion. Since the astrometric data is not evenly sampled during the whole period of the target system, the linear regression result, this is the red dashed line, or you can call it the 5-parameter astrometric solution, would thus deviate from the target system astrometry. So the deviation of the offset would be the error of the position, and the deviation of the slope is the bias of the proper motion. We conduct a Monte Carlo simulation to assess the influence of this unknown companion on barycentric correction. We consider a solar mass target star with an unknown companion. The x-axis is the period of the companion, and the y-axis is the mass of the companion. The color is the estimated magnitude of the radial velocity bias induced by this companion. And this radial velocity bias is normalized by parallax in the unit of microarc second. So for a target which is 10 per second from us, the value of this radial velocity bias should multiply by a factor of 100. And the radial velocity observational baseline is assumed to be 10 years for hops, and the measurement of the astrometry is assumed to be 3 years for Gaia mission. And the light emitted by the companion is also considered in this simulation. We can find a trend that the companion with larger period, that is the right part of the plot, and a larger mass, that is the upper part of the plot, the companion with this property have a larger influence on the radial velocity. So for a target with for a substellar companion with about 0.1 solar mass, they would introduce a bias with the magnitude of about 10 centimeters per second for a target which is 10 per second from us. So it have the same scale with the radial velocity signal of Earth's twins. And it's very important for us to consider this effect. And we need to notice that for the companion with larger mass, this effect is not very significant because the light from the companion would balance the reflex motion of the target star, and it would decrease the variation of the target system's photocenter, which leads to a smaller astrometric bias and radial velocity bias. So the objective of this work is to first correct the bias in Gaia DR3 astrometry due to nonlinear motion and reconduct barycentric correction on the RV bank dataset using corrected astrometry and PEXL. The RV bank is a user-friendly dataset reduced from HOPS data, and PEXL is a software for barycentric correction, which considered all the first-order and second-order relativistic effects. So it's a very precise package. Let's see how can we do it. Here is the log likelihood of the model. There are several terms, don't afraid of it. The first term is the likelihood of the model, and the second term is just a prior, or you can call it a regularization term if you like. And the last two terms are just normalized constants for the posterior. And A and B are the parameters in the model, and A is just the correction for the astrometry, that is the correction for RA, DEC, and position. And we need to notice that the correction for parallax and relative radial velocity is not considered in this work because according to an order of magnitude estimation, the effects of the parallax and radial, the absolute radial velocity is just about 1 micrometer per second, which is not important for detecting Earth twins. And B is just an offset. The VR is the radial velocity data provided by HOPS RV bank dataset, and J hat is the Jacobian of the radial velocity data with respect to the correction A vector A. And the sigma here is the error bar provided by HOPS RV bank dataset, and the S here is the error bar provided by Gaia DR3. So since it's a linear model, we can easily optimize it by taking the derivative, or you can see the gradient with respect to the parameters and set the gradient to 0. The effect of this posterior is to decrease the scatter of the radial velocity. So let's have a view of the results of this correction. The correction for the targets is shown in this corner plot. We can see that the quantity will be correct, that is RA, DEC, and proper motion. They are positively correlated. This is because for a target with larger companion, the amplitude of abscissa would be larger, thus leads to a larger bias for all directions. The result matches this intuitive. And to clarify the effects of the correction, let's take a look at some specific targets. This is the change of radial velocity of GJ506 after the astrometric correction. And this plot is obtained by taking the difference of the corrected radial velocity and the raw radial velocity provided by the HOPS RV bank dataset. And we can see that the change is just a linear trend superposed with an NU signal. And the amplitude of the NU signal is about 2 centimeters per second, which is important for detecting Earth twins. we can calculate the periodogram for the target after the correction to see whether it really decreased the NU signal as we introduced before. So this is the difference of the periodogram after the correction. And we use Bayes factor periodogram to judge whether the signal with certain period exists. And we can see that the signal with a period of 365 days and half of it is significantly decreased after the correction. Besides that, all its 3 confirmed exoplanet signal is more significant after this correction. And let's have a look at another target. In 2018, research proposed a candidate super-Earth orbiting the snow line of Banner star. The period of this super-Earth candidate is about 230 days. Let's see the change of periodogram after the astrometric correction. You can still see that the NU signal is less significant, or you can say suppressed after the correction. And the signal of the super-Earth candidate is more significant after this correction. So the conclusion is that astrometric correction is important for stars with wide orbit massive companion. This is the result of our simulation. And our method can correct the astrometry and radial velocity of nearby stars, which is shown by the example of GG506 and Banner star. And finally, we can model the motion of solar system and target system simultaneously in future work. This is because our method is to correct the astrometric bias caused by nonlinear motion. However, we simply use a linear model to correct it. So modeling the nonlinear motion of the target could give a better result for the targets which companion's period is longer than the baseline of radial velocity observation. That's all. Thank you.
Thank you for that lovely. Oh, okay. There's a very eager hand in the room. Thank you for that wonderful talk.
Oh man, I love barycentric corrections. This is great. So I just want to make sure I understand, because this is really important, I think. We know getting the astrometry wrong will introduce annual signals and aliases and be degenerate with such planets. Do I understand that from the actual published RVs, you have detected a previously unknown massive companion around these 2 stars? And if so, can you say something about its properties based on the corrections you've made, or do I misunderstand?
No, I didn't detect any unknown companion. The motivation is to decrease the scatter of the radial velocity. You can see the model is that you need to decrease the scatter of the radial velocity. Why can we do it? Because in theory, we can decompose the standard deviation, or you can call it the weighted standard deviation of the radial velocity. So the noise would make some contributions and the signal would also make some contributions. So if they are separate from each other, when you make the total standard deviation lower, you mean that you decrease some noise. This is the motivation. So we just lower the scatter of the total standard deviation
By correcting the astrometric solution.
Yeah. By correcting the astrometric solution.
Okay, so you found an error in the, you think you have a better astrometric correction, which may or may not be due to unseen companions or something?
Yeah, so you're correct. You can see that some of the target has a realistic large astrometric solution. This is just because we didn't find the unknown companion. We just use some linear model to correct it. So for a more complex model, you can model the solar system and the target system simultaneously and get a full understanding about whether or not the system indeed have a unknown companion. This can be checked by some statistics method, for example, the Bayes factor or something like that. Yeah, I think it's in the future work. We can do it to model it and check whether there is indeed a unknown companion causing the bias of astrometry. Yeah.
Wonderful. Okay, let's thank Yicheng again for a wonderful talk.